Okay, physics review number 1. This one's going to be long. Okay, I was hoping to get all of the optics chapter in, but that's just not going to happen. Okay, so chapter 1 was talking about optics. We started with waves. So when we have waves, we have this type of wave, and then we have this type of wave. So this is a transverse, and this is the longitudinal. Right? Think of this as a spring. Bing. You collect it, it bounces back and forth. Think of this as a rope that you're flipping out. They're both periodic. That's my cat talking. They're both periodic, which means they repeat. So this one has a pattern like this, boom, boom, and then it repeats. And it repeats. We should know what that is because we just did that. It's called a sinusoidal function. This one has the same thing. This grouping of 3 will repeat, will repeat, will repeat. Okay, that the waves are always that way. So and then we have lambda, which is the wavelength. Wavelength is the distance between, like the distance for one complete cycle. One complete cycle distance. So it is measured in millimeters, micrometers, meters, centimeters, whatever you want to call it. It is a distance measurement for wavelength. And then we have wave period, which is the time of one wavelength. So in other words, how long does it take to complete that 5 centimeters or that 10 centimeters? All right. Now you can also get the period by multiplying the how many cycles. So the time to take how many cycles. Okay, so that will give you the period as well. Instead of measuring one cycle, you can say, oh, there's 10 cycles, but it took 10 times as long, so it should give you the same answer. All right, and then we have frequency of every single wave has its own frequency. So that refers to how many cycles you fit in a time. So number of cycles over a particular period of time. So if it's 10 cycles per second, 20 cycles per second, okay? And for frequency, we use the unit hertz, which is per second, right? Which is per second. So every second for over second, okay? So number of cycles over every second. All right. So that's a very fast review of properties of wave, definition, and terminology, nomenclature for waves. Now we get to light waves. Light waves are linear. Okay, they're also electromagnetic. That means that they do not need a medium to travel through, right? If you talk about sound, sound has to travel through something, whether it's air, whether it's water, whether it's jello, whatever. Think about sound moving through something. If there was nothing, if it was vacuum of space, sound would not be able to travel. Light, because it creates its own electromagnetic field, it can travel through anything. It does not need a medium to travel through. All right. We also know that the speed of light is 3 times 3.0, or 3 times 10 to 8 meters per second. Okay, so that is c. And then light travels in a linear propagation. That means it travels in a straight line. You cannot, sorry, I shouldn't say you cannot. We don't generally talk about bending light. You need a huge gravitational force to be able to bend light because it is matter, it will move. So we're talking about light traveling in a straight line, everything that we're doing. Okay, so if we have a point source of light, then that will create a solid shadow. However, if we have a wide source of light, which is an extended source of light, then we will get not only will we get a shadow, we will get a shadow here, and we will also get on either end of it, kind of like a lighter shadow. So this is called the penumbra. Okay, so on either side of the darker shadow, you will get a lighter shadow. So if I hold my pen really close to the board, right now you get a nice solid shadow because it's so far away from the light source that it treats it, or so close to that only the parallel beams are hitting it. As I move it away, you start seeing a solid shadow and then a lighter shadow on either side. Okay, that's because now there's more of that light that goes around the pen to hit the board. Okay, now light will do one of three things. Okay, light will, when it hits something, light will reflect, it will refract, or it will be absorbed. Okay, so if you have this surface right here, if I move the light in front of it, boom, you probably see a reflection in the camera. So that is a reflection. The light hits it, it bounces back into your face. When it refracts is when the light hits something, like going through different mediums, so air into water, it will change directions. And then absorption is right now the light's hitting this wall, it is going into the wall, it's not bouncing back. So if I was standing on the other side of the room and I shine the light at the wall, it will not bounce back and hit me in the face, right? I will not see a bright spot. Whereas if I put the light in front of this reflective surface, the bright spot will hit my eye. Okay, so it can do one of three things. This video, we're only going to talk about the reflection because there's not enough time to talk about the rest. We'll get to that next video and so on. Okay, so, oh, this is drying out already. So light reflection. I mean, remember, it's bouncing off the surface. So you can get a specular reflection or diffuse. Okay, think of specular reflection as a mirror. The light comes in, bing, bing. So it comes in, bounces up, comes in, bounces up, bing, right? And then think of diffuse as a broken mirror. So light comes in, this one might bounce this way, this one might bounce this way, and this one might bounce this way, this one might bounce backwards. Okay, so you do not get a regular reflection. That's called diffuse. If you get specular reflection, it's a flat, perfect. Early morning on the water, before any waves happen, you get nice reflection. Once you get ripples in it, you don't see things reflect nicely. All right. In a specular reflection, there are a bunch of physics things that we can apply. So the first law of reflection says that the reflection and the incident ray are on the same plane. Think of it as this way. If I had a flashlight up in this corner right here, and I turn it on, and the light travels down here, and I had a mirror down here at the bottom, it would bounce off the mirror, but then it would come back up along this whiteboard. It will not come down the whiteboard and then bounce off the whiteboard. So it travels in the same plane. So if I'm flashing like this way, the person standing over here will not be blinded by it because it goes this way. It cannot go here towards that person out there, right? And then the second law of reflection says that the angle of incident is equal to the angle of reflection. What that means is, if there's my surface, there's my light coming in, there's my light going out. If I draw the normal, this is my angle of incident to the normal, and this is my angle of reflection, and they must be equal. Okay? All right. So that is a flat mirror reflection. The specular reflection will always be that way. Just simply put it in, drop it perpendicular to normal, and it goes out. Okay? So now we look at a curved reflection, curved mirror. So if we have a circular or parabolic or spherical mirror, we get a slightly different type of reflection. So if we have a curved mirror and the light source is coming from here, boom, any light source that goes in directly will come straight back. So it comes in, comes straight back. If the light source comes in like this, it will no longer come straight back because now it has to respect the law of angle of incident, angle of reflection. Here, if I draw a perpendicular, boom, it is at 90 degrees to the mirror. So therefore, 90 degrees in, 90 degrees out. Here, if I draw the tangent to the circle at that point, now, here's a normal, is now coming in at this angle, which means it's going to bounce back out at that angle. Down here, boom, it will bounce back out at that angle. They will all meet at the focal point. Okay, the key here is that I draw a tangent, draw the normal to the tangent, and then I measure my IR. Okay, and draw those two and measure it out, and it should reflect always to the center. Okay, and this is how we can create real and virtual images. Real and virtual images. So when we're talking about images created by light, by projection, we have real versus virtual. So a real image is the natural extension of, natural collection of the light. So convergence of the light. So bounces off, boom, it converges here. If I had an image in front of here, I'll be able to generate an image here. Okay, because that's where the light would reflect. Okay, virtual would be the fictitious, you want to call it? Yeah. Fictional, fictitious extension of the light ray. Right? So it does not create an image. We have to sort of mentally construct that image based on what it might look like somewhere else, because the light itself does not make the image. Okay, we can do it using pen and paper and drawing it out, but the light itself will not create that image. Okay? Or our brains can create that image, but the light will not make that image. Our eyes and our brain can create the image. So an example of the two would be, a real image would be if you had a projector with a picture in front of the light source, shines out, and it creates an image on the screen. That's a real image. If I were staring at a mirror, what I'm actually seeing is my brain's construction of those light rays on the other side. So I'm not seeing a real image, I'm seeing a virtual image. My brain's creating that image for me. All right? Okay. So if I were to, right, so when we have an image, we can have there are several properties. We can talk about the orientation. So it can be upright, it can be upside down, it can be rotated, it can be flipped around. Okay, those are the properties that you can have for any image. The size of the image, it can be bigger, smaller, or the same size. And the size of the image talks about magnification. So in other words, the height of the image that you see divided by the height of the original gives you the magnification that you create in that image. Okay, and then the position of the image, it can either be in front of the mirror or behind it. Okay, so now we're talking about, when we talk about looking at my reflection, it is a virtual image behind the mirror. So it looks like I'm inside the mirror. Okay, it's the same size and it's upright, but it's virtual and it's behind the mirror. All right. So if I'm looking at, so here's my eye, and then let's say I have a mirror here, boom, and then I hold underneath here, a picture of a lovely tree. When I look into that mirror holding a tree, I see the tree on the other side of the mirror. Well, why do I see the tree on the other side of the mirror? So the first thing I have to understand is that what I'm seeing is light that is bounced. So the sun somewhere, light source, hits the tree, it bounces off the tree into the mirror, and then it comes back towards my eye. But it doesn't come back towards my eye like so, right? Because then it doesn't respect the law of incident and reflection. What actually happens is my brain creates this extension of the line, doubling it, so it goes like this. And then I look here to there and to there. So this is what I see. That's why I see it down below me further into the mirror. So now if I connect the top with the top and the bottom with the bottom, I am now respecting the law of incident and reflection, incident and reflection. Okay, so this would be a virtual image that is same size and upright. So how do we create an image? How do we construct the image on a curved mirror? So if we have a curved mirror, whether it's curved in or curved out, doesn't really matter. So if we have, the floor, and then we have our tree here, okay? Oh, sorry, every curved mirror has a focal point, right? So every curved mirror has a focal point in which it is measured. That's where all light's going to reflect in, and then that is called the center of curvature. So if I take my finger and I draw a big circle, that would be the center, and the focal point is going to be center over 2. So it is half the length from the center to the edge is your focal point in which it will reflect. So if we want to create the image, what we do is we draw a line parallel going into the mirror, and then from that it will reflect into the focal point, right? Because we already decided that was going to happen. And then we do the same thing. We go from the top through the focal point to the mirror, and then reflect it out parallel to this line. And the third one is we draw through the center, and it should all meet in the same spot, which means that is where our image of our tree would be. Okay, so if you were able to shine a light off a round mirror, you get an inverted, smaller, real image of the tree. Right? So now if we have the tree on a curved mirror, so now the mirror is curved on the other side, same thing. Draw a parallel line in, goes through the mirror, but it doesn't go through the mirror, so we draw a fictitious reflection. Boom, because that kind of mirror will reflect light out. And then we draw a line through the focal point, so boom, then it comes back parallel. And then the last one is through the center. Oh, that's terrible. So if I connect it should be right here. That one didn't quite connect, but so that would be a virtual image, but it would be upright and it would be smaller. Okay? And then to figure out the actual numbers, you would go 1 over f equals 1 over do plus 1 over di. Okay, so if they give you the distance to the object from the mirror and they give you the focal point, then you can figure out what the image is and vice versa and back and forth. Okay? Now there's something called spherical aberration. That means that if you reflect light at the very edge of the mirror, somewhere up here, it will not behave properly. It will not reflect through the focal point mark, it'll reflect closer to here. So if you want a true accurate measurement, don't use the edges. So even if I up here, it will not reflect down here, it will reflect closer to there. That's called spherical aberration. All right, that should be it for reflections, and then next video we'll continue with refractions, and I'll hopefully get into chapter 2, or sorry, unit 2. All right, okay, that's it.